In this video, we will discuss the summary output of the OLS function from Python StatsModels library, using a simple example. We will also explain what some of the attributes mean and how they are calculated. This video assumes we are aware of fundamentals of multiple linear regression using OLS. So, we will start by building a regression model using OLS, and go ahead to understand the summary output of the OLS regression model. We will also see how some of the parameters are calculated. We read a simple dataset with 3 independent variables: age, gender, and BMI. Our target variable is medical expense. We separate the independent variables and store them in a variable x. We store the dependent or the target variable into y. Finally, we fit our OLS model and print the summary output. Let us now see each of the parameters in the output from the beginning. We see the dependent variable is medical expense. Below that, we see the method used to build the model, and the date and time the model is built. This is a very simple information, and is not of much importance to us. Next, we get to see the number of observations our dataset has. We also see the degrees of freedom of the residuals. The df residuals is calculated by n-k-1, where n is the number of observations, k is the number of independent variables. The df model is the degrees of freedom of the model, that is the number of independent variables. Before we see other parameters, let us predict the values by passing the x to the predict function. We get to see the predicted values. We will be using these predicted values for calculating a few parameters. Next, we see the r-squared value. The r-squared value is 0.174, which says that the linear combination of independent variables explains 17.4% of the variance in the target variable. R-squared parameter ideally takes value between 0 and 1, and a value closer to 1 is preferred. Now, let us see how to calculate the r-squared value for the model. We calculate the residuals by calculating the difference between y-actuals and y-predicted. Then, we compute the sum of squared residuals using the np function. We print the SSR value. Next, we calculate the total sum of squares centered around the mean. Which means, we subtract the mean of target from each of the values in the target variable. With this, we get the total sum of squares centered around the mean. Finally, with the SSR and the centered TSS, we calculate the r-squared value. You may tally this computed value with the OLS output. Now, let us see how the adjusted r-squared is calculated. Adjusted r-squared is the penalized version of the r-squared. It considers the degrees of freedom of residuals, that is n-p-1, where n is the number of observations, and p is the number of predictor variables. We get the number of observations from the shape attribute. Using the degrees of freedom of residuals, number of observations, and the r-squared value, we get the adjusted r-squared value. You can tally the value of the computed adjusted r-squared and the adjusted r-squared as given by the OLS output. Now, let us take a look at the F-statistic and the p-value of the F-statistic. If p-value of the F-statistic is greater than 0.05, there is no evidence of relationship between any of the predictors and the target variable. On the other hand, if p-value of the F-statistic is less than 0.05, there is at least one variable that is related to the target variable. Let us now see how to compute the F-statistic and its p-value. We compute the residuals with the actual target values and predicted target values. Then we compute the sum of squared residuals. We then consider the mean-centered y to compute the explained sum of squares. We store the value in ESS. Using the explained sum of squares and model degrees of freedom, we calculate the mean squared error of the model. Then, we compute the mean squared error of the residuals by dividing the explained sum of squares by the residual degrees of freedom. Finally, we calculate the F-statistic by dividing the mean squared error of the model by mean squared error of the residuals. We use the stats library to compute the p-value of the F-statistic. We pass the F-statistic, model degrees of freedom and residual degrees of freedom to the required function. You can tally the output with the F-statistic values in the OLS output. We now look into the log likelihood. The log likelihood is a measure for fit of the model with the given data. Log likelihood is useful when we compare two or more models. The higher the value of log likelihood, the better the model fits the given data. The log likelihood value can range from -infinity to +infinity. Let us now see how the log likelihood is calculated. We consider the number of observations in the dataset. We calculate the residuals by calculating the difference between y actual and y predicted. Taking the residuals into consideration, we calculate the SSR. This is something we have done earlier as well. Finally, we take into consideration the number of observations and SSR to compute the log likelihood. You may now compare the computed log likelihood value and the log likelihood value that was produced by the OLS output. Next, we look into AIC information criterion and Bayesian information criterion. In short, AIC and BIC. AIC and BIC are used as criteria for model robustness. The model with lower AIC and lower BIC value provides a better fit. Let us calculate the same using Python. We have already computed the log likelihood. So we use the log likelihood value to compute the AIC and BIC. We consider the number of features as 4 for our model. So, we compute the AIC value as -2 times the log likelihood plus 2 times the number of features. We get an AIC value of 410. Let us now calculate the BIC value. We consider the number of observations. We compute the BIC value as -2 times the log likelihood plus number of features times log of number of observations. We get a BIC value of 413.98. Let us tally the same with the AIC and BIC value in the OLS output. Now that we have covered a few parameters to evaluate the model as a whole, we deep dive into the parameters related to the features. To start with, we take the coefficients and see how the coefficients for the features are calculated. Note the closed form equation of linear regression. The derivation of this equation is out of the scope of this video. So, we simply take the closed form equation and compute the beta coefficients. We filter out the independent variables into x and add the constant. We also filter out the dependent variable into y. Now, fit the x and y into the closed form equation. X squared is x transpose times x. Then we compute the inverse of the x squared. Finally, we multiply the x inverse with x transpose and y to get the coefficients. Compare the computed betas with the coefficients in the OLS output. Let us move to see how the standard errors are computed. We first compute the variance of the residuals. Then, taking the variance of the residuals, we compute the variance-covariance matrix of the coefficients. From the variance-covariance matrix, we need only the variances. So, we consider the diagonal elements from the matrix. Finally, we compute the square root of the variance to get the standard errors of the coefficients. You can tally the standard errors that we have computed manually with the standard errors specified in the OLS output. We now look into the T-statistic and its p-value. P-value is calculated from T-statistic. When p-value less than 0.05, it indicates a strong evidence against null hypothesis, which states that the corresponding predictor has no effect on the target variable. We have earlier computed the beta coefficients and the standard errors. We divide the beta coefficients by the standard errors to get the T-statistic. Now, we use the stats module to pass the T-statistic values and residual degrees of freedom to estimate the p-value. We multiply by 2 as it is a two-tailed test. You can tally the T-statistic and the corresponding p-values with the OLS output. We now take a look into the confidence interval and see how these values are computed. A 95% confidence interval for the coefficient says that the interval has a probability of 95% to contain the true value of the beta coefficients. In the formula shown, the t-value inside the square bracket is the critical value that we get from two-sided students' t-distribution with n-k degrees of freedom. Before we get into the calculation, let us find out the t-critical value using an online calculator. We consider a two-tailed test. 16 degrees of freedom, 5% significance level, and 8 precision output. We get the t-critical as 2.11990529. We compute the lower CI and upper CI with the shown formula. The SE inside the bracket is the standard error that we have computed earlier. You can tally these values with the OLS output. Omnibus test checks the normality of the residuals. If the value is 0, it means the residuals are perfectly normally distributed. We simply call the normal test function from stats module and pass the residuals to get the statistic and its corresponding p-value. You can tally the statistic and its p-value with the OLS output. Skew values tells us the skewness of the residual distribution. Normally distributed variables have zero skew values. The rule of thumb says, if the skewness is between -0.5 and 0.5, the data is fairly symmetrical. If the skewness is between -1 and 0.5 or between 0.5 and 1, the data is moderately skewed. If the skewness is less than -1 or greater than 1, the data is highly skewed. Now, let us see how to compute the skew value. We can either use a direct available function or compute it manually. We will do both in this demonstration. Let us generate the model summary output once again and see the skew and kurtosis value. We compute the residuals. We import the stats module and call the skew function. We pass the residuals to the skew function to get the skew value. Note the skew value returned by the skew function and the OLS output. Now, we demonstrate how to compute the skew value manually using moments. We calculate the second order, third order, and the fourth order moments using stats.moment function. We pass the residuals to the moment function. We also pass the order as one of the parameter to the moment function. Then we finally calculate the skewness using the third moment and the second moment. Now that we have seen how to compute the skewness, let us see how to compute the kurtosis, both using available function and manually. We use the stats.kurtosis function and pass the residuals to it. The Fisher parameter is set to false. When Fisher is set to false, Pearson's definition is used. In order to compute the kurtosis manually, we use the fourth and second order moment. We now move to see how the Durbin-Watson and Jarque-Bera statistic are computed. We will also estimate the p-value for the Jarque-Bera statistic. Durbin-Watson statistic provides a measure of autocorrelation in the residual. If the residual values are autocorrelated, the model becomes biased. The DW statistic ranges from 0 to 4, with a value of 2 indicating zero autocorrelation. Values below 2 mean there is positive autocorrelation and above 2 indicates negative autocorrelation. We calculate the residuals. We compute the difference of residuals, as shown in the formula. We then compute the Durbin-Watson statistic using the difference of residuals and the squared residuals. You may tally the Durbin-Watson statistic with the OLS output. Now we see the computation of the Jarque-Bera statistic and its p-value. We use the previously calculated residuals, skewness, and kurtosis. We input the required values to the Jarque-Bera formula as shown here. Finally, we calculate the p-value associated with the Jarque-Bera statistic. You may tally the computed values with the OLS output. Condition number is an indicator for multicollinearity. A high value indicates presence of multicollinearity. The condition number for the matrix X, as reported by StatsModels, is an indicator for numerical problems that can be caused by either multicollinearity or bad scaling. We take the independent variables with the intercept and transform it into a NumPy array. We compute the eigenvalues. Condition number is given by the square root of the ratio between the maximum eigenvalue and minimum eigenvalue. You may tally the computed condition number with the OLS output. In this video, we explained how the parameters that are shown in the StatsModels OLS output are computed. Please feel free to comment on our videos and do subscribe for future video notifications. Happy learning!